In this video, we're going to be talking about titration curves. I made a previous video about basic titration calculations and how to think about the idea of titration, and this is in some ways a continuation of that. Our learning goals for this video are to use a simulation to visualize titration, to analyze a titration curve to determine how much acid or base was added to neutralize a solution, and to describe what is happening at the equivalence point of a titration curve in terms of H plus or OH minus ions. Let's examine this simulation a little bit more closely. I think it's a great way to visualize what we are looking at when we are looking at a titration curve. Remember, titrations can be used to find the composition of an unknown acid or base by adding a recorded amount of a known base or acid. Many titrations are acid-base neutralization reactions. The equivalence point, in this case pH 7, of this reaction occurs when the moles of acid and the moles of base in the solution are equivalent. So the equivalence point on an acid-base titration curve is the point at which the pH is 7. It's often also what we call the inflection point of the graph, the point where the pH rapidly changes. Notice this green dot represents the pH of the solution, and as I drag this red dot down, it will represent titrating or adding some more acid to the solution. So I'm adding acid. We can see some acid particles appearing at the top. That means that I'm increasing the concentration of H plus ions. And we can see that at the equivalence point, when the pH is 7, I have an equal concentration of acid and base, of hydronium and hydroxide ions. If I continue moving past the equivalence point, my solution will become acidic. I've added way more acid than base. Let's think about how a titration curve could be useful to us in other circumstances, besides just looking at a simulation. Here's a titration curve showing 50 milliliters of an unknown strength acid, which was titrated with 0.5 molar NaOH, base, sodium hydroxide. Now, from just looking at this problem, we may not initially think we have enough information to solve for the strength of the unknown acid molarity, or Ma. Because just from looking at the given numbers in the problem, I know that I have 50 milliliters of acid, but I don't know the molarity of the acid. And I know that I'm titrating it with 0.5 molar, so the concentration of 0.5 molar base, but the question isn't telling me the volume of the base that I used. This is where titration curves come in. I can determine how much base I needed to use by studying my curve. I can find my equivalence point, the point where the pH was 7. That's the moment that the reaction was completely neutralized. And if I trace that down to the x-axis, which is showing what volume of NaOH had been added at that time, I get 25 milliliters. So my volume of my base that I would want to use would be 25 milliliters. Solving for Ma, I get 0.5 times 25 divided by 50. So the molarity of my acid must have been 0.25 molar. Let's try a practice problem that you will do. Take a look at this titration curve. This time we are starting with a base. We have 4.5 milliliters of an unknown strength base, and we are titrating it with 0.15 molar hydrochloric acid. Your job is to use the titration curve to determine the concentration of this unknown strength base. So take a look, see if you can work it out. Pause the video if you need more time, and I will go over the answer. So it all starts here with reminding ourselves of our equation from table T that we would need. The molarity of the acid, which we know is 0.15 molar, times the volume of the acid that we use. We're going to look at the titration curve in a moment to figure that out, is going to be equal to the molarity, or the concentration of the base, times the volume of the base, 4.5 milliliters. So the equivalence point is about here. If I read my x-axis, that would be about 3.4 milliliters of acid used to get the solution neutral. So I would do 0.15 molar acid times 3.4 milliliters of acid equals MB, the molarity of the base, that's what we're trying to find, times 4.5. So when I multiply 0.15 times 3.4 and divide by 4.5, I should get 0.11 molar as the concentration of my base. Now this makes sense because I needed to use a little bit, or there was a little bit more base than there was acid that I used. There's 4.5 milliliters of base, and I only had to use 3.4 milliliters of acid to neutralize it. So it makes sense that the base would be a little bit less strong than the acid because I have a little bit more base in order to be neutral. If we had exactly the same concentration of acid and base, we would also need the exact same volumes. Here's another problem for you to try. A student is to determine the concentration of an NaOH solution by performing two different titrations. In a first titration, the student titrates 25.0 milliliters of a 0.100 molar sulfuric acid with sodium hydroxide of unknown concentration. In a second titration, the student titrates 25 milliliters of a 0.100 molar hydrochloric acid solution with a sample of sodium hydroxide. During the second titration, the volume of sodium hydroxide added and the corresponding pH value of the reaction mixture is measured. The graph below represents the relationship between pH and the volume of the NaOH added for this second titration. So based on this graph, you're going to determine the volume of sodium hydroxide used to exactly neutralize the hydrochloric acid. And this is referring to the second titration that was described above. Then you're going to think about what the color of phenolphthalein indicator would be if it were added after the hydrochloric acid was titrated with 50 milliliters of sodium hydroxide. So take your time here, pause the video if you need more time, see if you can work out these questions. So let's take a look at the graph. If I'm following the graph, it looks like when the pH is 7, the volume of NaOH added was 25 milliliters. It's a pretty straightforward equivalence point there. Now, to think about, this is a little bit tricky, the second question. The color of phenolphthalein indicator, if it were added after HCl was titrated, here's the keyword, with 50 milliliters of NaOH. 50 milliliters is all the way over here on that titration curve. That means that this question is asking me, what color will phenolphthalein indicator be if the pH is between 12 and 13? Phenolphthalein is right here on table M. It has a pH range, color shifting range that goes from colorless to pink as the pH range increases above 8 and 9. So if the pH is below 8, it is colorless. If the pH is above 9, the solution is pink. So if the pH is 12, because we've added 50 milliliters of NaOH, this solution indicator would be pink because the pH would be greater than 12. Read carefully there, right? Because if they were asking what the indicator would look like at the point that the solution was neutral, it would be clear. But if we've added 50 milliliters of NaOH, then it would be pink because the pH would be 12. Let's check back in on our learning goals before we go. Hopefully, using the simulation helped you visualize what's going on during a titration reaction a bit more, and also helped you see how a titration curve is really just plotting out the volume that needed to be added of either an acid or a base to bring the solution to a pH of 7, even just for a brief moment. Finally, hopefully this video helped you understand what's happening at the equivalence point, that point where the pH is exactly 7. Nice job today.